Yeah, how's it going, mate? I'm Obsidian Zenon. Must have been a couple of years ago now, I built this arc lighter out of an old torch that broke because it was a piece of junk. But recently it just broke. The circuit's fine, but the case, because it was held together with electrical tape and hot glue, it's just sort of fallen apart. So I thought I'd make a video on just making a new case and adding a little battery indicator as well. So the circuit for the arc lighter isn't exactly complicated. That's crude drawing, but that's literally all it is. And you just feed it with 4.2 volts 18650 cell, and yeah, that's it. And I thought, okay, well, I may as well add a battery indicator. It lasts for months on end, the battery, but I just thought, hey, you know what, it would be a good project. So you can see I've just got this all just spider webbed around here, and I'll just demonstrate for you quickly. This may cause some interference, we'll see. So yeah, it's annoyingly loud. Sorry to all you headphone users, but yeah. So it turns out for a simple, LED bar meter for a battery indicator, there already exists quite an old chip for it. It's called the LM3914. I don't think it originally comes from TI. I'm pretty sure it comes from another company that I will probably put up here later. But yeah, I'm just going to read through the data sheet on here. It's fairly long. I'm just going to get an idea on how that works, and then hopefully I can design a circuit. And then once I design a circuit and get all the stuff ordered in, then I can, I guess, 3D print a new case or find something to make the case out of. I apologize for the pixely screen. I don't have a printer, so I can print this out, and my monitor's only 1080p, so yeah. So it looks like we have got, this is just an example for measuring 0 to 5 volts, it looks like. I've got 10 LEDs, and that it looks a fairly simple circuit. The lithium ion battery I have is, it's wrapped and capped on tape to stop shorts and stuff, but it's protected, so it's got some kind of I guess a chip inside of it that prevents overcurrent, overcharge, over discharge, things like that. A lot safer than using an unprotected lithium ion. So very interesting. JCar, the website, didn't have the data sheet for the specific battery I have, which is really interesting. But I have this old, probably 4-year-old JCar catalog right now, and it's got the specs on here, so we can have a look at that. And so just looking at this, we can see that we have cutoff voltage for charging of 4.2 volts, so that's our maximum voltage, and our minimum voltage seems to be 2.75 volts. I might keep it at 3 just to be safe, so we don't have a cutoff in the middle of using it. So I will test the lighter between those two voltages, and we will see if there is any noticeable difference, if I have to cut it off earlier or later. We'll see about that. So I'm just going to bump my power supply voltage up to about 4.2 volts there, you see. And I'm going to start it, and then I'm just going to turn the voltage down until the arc looks weaker. I may disconnect and reconnect as well, just because arcs can be sustained over lower voltages if they start at a higher voltage. But we'll start at 4.2. Another headphone warning, I might turn the volume down on this. And I'll just start turning it down. Okay, well, we're at 3 volts, and there is still an arc being sustained. I can also smell some ozone being generated, so if you are doing this, be careful about that. Make sure you have lots of ventilation. I will start it again at 3 volts. And no arc was formed then, so I will bump it up to 3.2. Just barely. So if I just write this down, our range will be from 4.2 volts to 3.2 volts. and so we want all our LEDs to be lit up here and none of them to be lit up, or maybe one of them to be lit up here. Okay. Alrighty, so it's been about a while, probably 3 weeks, mainly because I've just had a bunch of weekends where I haven't been able to do this. We got a new radio while I was waiting, but anyway, I got the circuit working. It's a little bit dodgy. The voltage range isn't exactly what I specified due to less than ideal conditions in real life, as opposed to a schematic, but I've gotten it to go from 3.7-ish volts, and I'll just turn it up, and you can see the scale is going up there. Sorry about the bad angle. And you can see the maximum is about 4.2 volts. I'll have to tweak this a little bit, but you can see the current draw is a little bit high, but it shouldn't matter much because the circuit is only going to be on for maybe 10 seconds at a time, and that's just a bad connection in the breadboard there, so don't worry about that. But yeah, I'll get this soldered up and then I'll explain the circuit to you. It may take a little bit though. Right, so the circuit's done 2 days later, and you're probably wondering at first glance how I got these 10 LEDs all wired up in this very thin space. I made it very thin so I could put it inside of the lighter, but you're probably wondering how I did that, and I will show you in a sec, but I first want to show you how it works, so give me a sec. Alright, so I've just got it precariously propped up here, and you'll see the LEDs are working, so I'll just turn the voltage up and down. So we'll go to where it's fully lit, which is 4.2 volts exactly, and we'll go down until one or none of them are lit. We'll go none, how about that? And that's about 3.6 volts, which is actually higher than what I wanted it to be. But it turns out with further testing, below 3.6 volts, the arc is a lot weaker for lighting flames anyway, so that's fine. So here's the underside, and so it's a lot neater than I thought it was going to be, so that's really nice. But you can see I've used thin enameled copper wire for the LEDs, and that was a real lifesaver there. I was wondering how I was gonna fit all 10 LED wiring in that thin space, because it just would not have happened with the solid core wire. As you can see here, that stuff is pretty thick, and 3 layers up, it's already full, because it's gonna fit into like a panel or something. I don't know yet, but yeah. And also tip for prototype hobby electronics: make sure you use this type of IC socket with the flat top, and sometimes they are gold plated. I don't think this one is, but it doesn't matter. Make sure they're flat like this. Don't get those industrial ones. The industrial ones are fine if you're doing a product that you're going to like mass produce and sell, but for prototyping, use this. It's far easier. You can probe the pins. You can it's much easier to pull out, just whatever. And you can also see I've made the resistor divider network like this to compact it, and that's the capacitor, just for purposes I'll talk about later. But now we're going to go into how this circuit works, and then after that we'll start doing the case, I guess. Right, so here is the final circuit, and you might be thinking, oh, that looks like gibberish, so I'm here to explain it for you, don't worry. So to understand this circuit, we're going to understand a simpler version of the circuit, which is this one. And to understand this, we need to understand how the chip works. Alright, so I've got 2 copies of the original National Semiconductor datasheet. On this side, I've got the block diagram of the LM3914, and on this side, I've got the pinout in case that helps as well. So we'll just go through the pinout first. So pin 1 is labeled LED number 1, and pin 18 is LED number 2, and the bar graph will go this way. This is an interesting way of doing it, but it kind of makes sense physically speaking, the way they laid out the components. But yeah, LED number 1 is at pin 1, and it goes this way, ends at pin 10. And pin 2 is ground, pin 3 is positive voltage, no worries. We'll skip pin 4, come back to that, and pin 5 is the signal input. Now, the signal input has to be, I think it's at least 1.5 or 1.8 volts less than the supply voltage. You can probably make that number a little bit lower, maybe 1 volt, which is what I've done, I think. But yeah, watch out for that. We'll skip pin 6, 7, and 8. And pin 9 is mode select. Mode select, basically, this chip has 2 modes. It has bar mode and dot mode. Bar mode is the mode I'm using, where the number of LEDs increases with the voltage. Dot mode is where there is only 1 or 2 LEDs lit at a time, and it just goes up the scale, which can save power if you have this on all the time, but in my case it doesn't really matter. Okay, going back to pin 4 and 6, we have divider low end and divider high end, or on this side it says R high and R low. You can see these are connected between this resistor divider of 10 resistors. Now, this resistor divider is what's responsible for making the bar graph work. Basically, if you have 5 volts here and 0 volts at R low, you'll have 5 volts decrease by 0.1 times 5 volts every resistor. So this will be 500 millivolts less, 500 millivolts less, so on, so on, so on, until this will be 500 millivolts, and that will be 0. As you can see, these are connected to comparators, and the signal input is connected through a buffer, so you can basically think of that as just a straight connection to the other end of the comparators. Basically, as the voltage goes up, the number of comparators with one of the voltages being higher than the other goes up, and so the LEDs start to turn on as we go up. Also, quick thing, you'll notice you don't need any resistors for the LEDs connected to the chip, and I'll explain why in a minute. Okay, now we've got that out of the way, we need to understand the reference voltage. So the reference voltage is interesting. You can actually adjust it using a resistor divider and connecting the reference adjust pin to this voltage divider here. And the output voltage is according to this equation, but we don't actually need to look at that. We first need to figure out R1, which can be figured out with this equation. So this is how we work out the current going through the LED, which is why we don't need a resistor. So current in LED is roughly 12.5 over R1. So we swap the values. R1 is 12.5 over the LED current, which in my case is going to be 5 milliamps per LED. That's just my specification. Yours may be different. So I'm going to do 12.5 divided by 5 milliamps, or 0.005, which will get me a rough value of 2500 ohms. And as you can see, that is the first value in my schematic here. So then we need to connect R high here, because that's going to be our high point, and we'll connect ref adjust here like it says in the adjusting voltage reference section. Now to work out this last one, you can see I've got 1426 ohms. How did I do that? Well, very simple. So considering that the voltage between pins 7 and 8 is 1.25 volts, it's actually, you need to look at the electrical characteristics, because the actual typical voltage is 1.28 volts. Here it says voltage reference output voltage, so make sure you watch that. So for this, we just need to figure out, to make this voltage what we want, in this case 2.1 volts, because I'm going to be halving the supply voltage to feed into the signal. We need to do 2.1 volts minus 1.28 volts. Okay, and we just use Ohm's law, so resistance is voltage, 2.1 minus 1.28 volts, divided by the current we need. So that the current will be 10 times less than what's going through each LED, 500 microohms as it says in the datasheet, plus the the current coming through pin 8, which is going to be, it will say in the datasheet, as voltage reference, adjust pin current, there you go, 75 microamps typically. So 575 microamps, and if you run the equation, we will get about 1426 ohms for my purposes. And you might be thinking, oh, that's all well and good, but how do you work out R low? It's not ground. Well, it's actually very simple. You just split this 2500 ohm resistor into 2 resistors to make a voltage divider that will equal your desired lowest voltage. If the voltage is lower than 1.28 volts less, then you'd split this resistor instead, but in my case, we're splitting this one. Now you can use a voltage divider calculator or do the equation myself. I prefer to do the equation myself, it's a bit simpler. And I ended up getting this. But you look at this and you go, hang on, that does not add up to 2500 ohms, and you're correct. This would normally be 560 ohms. But as you can see, I've got R low connected here, so I can get the lower voltage. But look, R high, R low, okay, they're connected across this resistor. Well, have a look. If we look at this, R high and R low, hang on, there's this entire resistor divider here. So basically, we've put this divider in parallel with this 560 ohm resistor. And there's no problem with that. You can just adjust the value of this resistor to make it seem like it's 560 ohms with the resistor divider in parallel. So we need to get the resistance of the resistor divider, which you'd think would be 10 kilo ohms, but it's not. It's actually, where is it? Voltage divider, 12 kilo ohms typically. So again, make sure you read the electrical characteristics. They are the true values. So if we can just use a parallel resistor calculator or do the equation yourself, 12 kilo ohms, get it to 560 ohms, you need a 587 ohm resistor, and that will equal to 2500 ohms if you measured it with it all connected up. And you can see there's our just voltage divider, that's half feeding into the signal pin. And we also, in this side of the schematic, which I've forgotten to add to the other one, is a 10 microfarad capacitor. That's just for stability of LED voltage. You don't have to add that, but I did just as a safety precaution. And there you go, that's how the circuit works. Alright, so it looks a little bit messy, but that's okay, it'll be in a case. But here, so you can see this is the circuit, and I just cut the board and glued the battery holder on the back with a on-off switch for the circuit, and also acts as a safety for the arc lighter, which I've also soldered on. These transformers you can get off AliExpress. There are hundreds of other videos about making arc lighters, so I won't talk about them. And then obviously we have the button for the lighter, so I'll just demonstrate this to show you that it does work. Alright, so we'll switch this on, and you can see there's our lights, and we'll press the button, headphone warning. And you'll notice that if I just go here, you'll see when I press the button, something funny happens with the lights. I'm not sure if this is because of some flyback business with this coil coming back towards the chip, or actually high voltages inducing currents inside the chip. I'm not really sure, but it shouldn't matter because this probably won't damage it, because I'll only have it on at like 10 seconds at a time, as I said before. And also I'm not reading the voltage while I'm pressing the button, so it should be fine. Now I just got to design a case for it, and yeah, I won't bore you with designing the case because that's not really the kind of stuff I do on this channel. But we'll go to that, and then we should be all done. Right, so I've got the parts slightly warped because I'm not that great at 3D printing, but it's hard to notice when you're holding it, so that'll be fine. And I've set a brass insert there so I can secure the transistor for the lighter right there, and some ventilation for the heatsink. So let's get started putting this in. Hey, check this out. So you can see this nut on the transistor. That was there before when the heatsink was attached, and it seems to have, I don't know, welded itself or like melted onto the heatsink, which is not a problem because I need it anyway, but that's pretty interesting. So, as you can see, I didn't make it the easiest thing in the world to assemble, but Right, so it is done, and yeah, it took a little while, but it didn't take as long as I thought it was going to take. And it works pretty well, so obviously I have to do the obligatory candle lighting test. So I've just got a regular tea light candle here. We'll turn it on, there's our bar graph, and we'll just light. Just lift it up. Ah, I just shocked myself, bugger. Ow, that hurt. And there you go. Might just bring it close to show you. And there it is. Okay, so I hope you enjoyed the video and learned something along the way, and possibly been entertained by my little slip up at the end there. But if you did enjoy the video, please like. You don't have to subscribe if you don't want to, but please like. It lets me know that my videos are good and I should keep going. And share this video with someone who you may think it'd be helpful for. See you guys.